Welcome back, ladies and gentlemen. So right now we're going to be taking a look at solubility curves. We've talked about solubility, we've talked about saturated, unsaturated, supersaturated, right? We talked about saturated, full, unsaturated, empty or not full, and supersaturated, more than full, because chemistry is weird and hard. Now we're going to be going into solubility curves, so a graph, which means numbers, all right? Let's take a look. The solubility of most substances increases as the temperature of the solvent increases. As we said, of course, that means that there is more room to put things because the particles spread out, other things are going on. For some substances, the reverse does occur, but generally speaking, more temperature, more solubility. As we discussed, of course, gases do not work that way. They're different. Consider the graph below. The solubility of all compounds except for Ce2SO43 increases as the temperature increases. So there it is. It's not below for me. It's on the right. But you'll see that everything is going up. Some of them are going up as straight lines. Some of them are going up as curved lines. But one of them goes down. So this is a solubility graph. And what we're seeing is the temperature down here, right? The temperature of the solution, and the amount of solute that I can dissolve. So for example, at 10 degrees Celsius, I can dissolve, for this potassium chlorate here, this orange line, I just read it across, and that's like about, what, 4 maybe? So I can dissolve 4 grams of this stuff if it's at 10 degrees. That's basically what it's saying. This is very similar to what we saw with the vapor pressure graphs back in the physical properties unit. You will notice, though, that the solubility is listed in grams of solute in 100 grams of water. So basically, because, like, I'm saying there's more room if I heat it up. Well, true, but there's also going to be more room if I just have a larger amount of liquid. Right? Like if I've got a cup versus a bucket, the bucket can hold more because it's a bucket. So we need a way to standardize it. So we standardize it to 100 because then it becomes a percentage. Okay. They are the effect of temperature on the solubility of a solid dissolved in a liquid solvent, specifically water, because we do a lot of that. A curve of best fit is drawn through all the points. From a solubility curve, we can predict the solubility of a solution at a specific temperature, or the temperature at which a solution will have a specific solubility. That is, we can extrapolate points on the curve to find information we need, or interpolate, depending on which one we need to do. Basically what happened is a whole bunch of chemists a long time ago sat down and they made solutions over and over and over again of hundreds of different possible combinations of materials at different temperatures. And then they wrote them all down in a book, and then they made some graphs of those. And then we can use that information instead of having to figure it out ourselves. So there it is again, right? Our solubility graph. This is one of many, right? I could give you a dozen of them. And the units here, as we mentioned, are a little bit weird. Okay, so solubility is the maximum amount of solute that can dissolve in a certain amount of solvent, or the amount of solute needed to make a saturated solution under those particular temperatures. A unit of solubility is usually done in terms of mass of solute per 100 grams of solvent. Since the density of water is 100 grams, it just turns into milliliters. So what does this mean? Again, it allows you to compare it by percentage, right? Like if it's half, 50%, whatever. What it means is basically just what do I need in order to make a saturated solution? That's the key thing here, right? Unsaturated, well, it's just not full, right? I could be almost full. I could be quite empty. Doesn't really matter, but we're talking about full. How do we make a saturated solution under any given situation? The solubility of a solute must be determined experimentally. As I said, everyone sat down, they did a bunch of experiments, and they wrote it all down. One method used to determine the solubility of a substance at a specific temperature is to add a known mass of solute to a known mass or volume of solvent. The mixture is then heated until all the solute dissolves. When the solute is dissolved, the solution is cooled until the first signs of solid crystals appear. The temperature at this point is recorded, and the solubility is converted to the desired solubility units. So this is the method that they used. Do you need to use this? No. We've already figured it out. We've written it down. All you need to do is understand how it works. So let's do an example. We've got 25 grams of a solute, and the maximum amount of solute that can dissolve in 40 grams of solvent at a particular temperature. Okay, so what we're saying is that I've got a container. Okay, so we've got here our container, and we're going to fill it with some sort of solvent. And we're going to say here that there are 40 grams of solvent. Okay, pretty straightforward so far. Then I'm going to take some solute and I'm going to put it in. So here's my solute. I'm going to put it in, and this is 25 grams. So what's the maximum amount that I could put in a second bucket that was 100 grams? So this is a bigger bucket, right? And this is going to be 100 grams. And I'm telling you that this will be saturated. It will be full. So how much do I have to put here in order to make this one full? Well, it's the same material in both cases. So this is actually just a simple ratio question. Put another way, over here we've got 25 grams over 40 grams. And this is going to be x over 100. Find x. The ratio of solute to solvent is the same for both of them. So you're just trying to connect these two together. You put all that together, what are you going to get? 62.5 grams. 62.5 grams. This was 1,000, right? This was a 1,000-gram bucket. If I did a third bucket here, and I have one over here that's like, I'm going to have to put in 625 grams. These are all related by a very consistent ratio. That's kind of it. It's just a measure of how much I can put inside. We've got a few more examples here. Different numbers, same idea. If 30.1 grams of solute, okay, so this one here isn't 25 anymore. Now this is 30.1. Can dissolve in 350 milliliters of water. Remember, water is 1 gram per milliliter. So instead of this being 40 grams of water, we're now at 350 milliliters of water at a certain temperature. What is the solubility of the substance in 100? Same basic idea. Just changing my numbers. This is still 100. Where's my black? This one here is 350. And this one here is 30.1. We put it all together, and what do we get? 8.6 grams for every 100 grams of water. So if I had 200 grams of water, it'd be 16.6 times 2, 17.2. Hopefully I did my mental math right. Next one. 39 grams of solute is the maximum amount of solute that can dissolve in 55 grams of water. What is the solubility? Same basic idea, slightly different numbers. I'm starting off with a situation that is 39 in 55. $39 in 55, what is it out of 100? $39 over 55, what is it out of 100? 70.91 out of 100, because 39 out of 55 is a pretty big amount. Basically, we're looking for percentages, right? What is the percentage of solute in the solvent here? So 39 divided by 55 will tell us a percentage. What's the percentage? About 71%. That's it. That's what we're doing. Not all the math has to be hard, guys. Sometimes it can be easy. Let's take a look at some solubility curves in a little bit more detail. Because as we said, it's all temperature dependent. Right? So we learned how to use the units. They're really simple. What about the temperature? Solubility is temperature dependent. We can find the solubility of a substance at various temperatures and plot this data on a graph. The result is what is known as a solubility curve. The diagram to the right shows an example of a solubility curve for potassium nitrate. There it is. Potassium nitrate in all of its glory. So at particular temperatures, we have a particular solubility. So down here, right, at 10 degrees, give or take, so down here at 10 degrees, right up here, it comes up to this part here, there, and then it reads across. That's about 20, sorry. So at 10 degrees Celsius, potassium nitrate, about 20% potassium nitrate will dissolve in the water. We keep going, right? If we're at, let's say, 60 here. So 60 is over here. We read 60 up, and we're going to see that it sits at 110. So we can fit 110 grams of the solute in 100 grams of water. So we're actually 110%. It's a little crazy. But you'll notice what it's telling us here. Under here is unsaturated. This green line is saturated, and above it is supersaturated. What's going on? Each point on the curve represents a saturated solution in potassium nitrate. So like, as I said, right here is saturated. All of these are saturated. So as I go up in temperature, I need to add more stuff to make it saturated. If I went up in temperature, but I didn't add more material, instead of following the green curve, I would just go straight across, right? I still got the same amount of stuff. I still got 10, and then I still got 10 here, I still got 10 here, I still got 10 here. And what we can see is that from like this part here at about, what is that, 30 degrees, 40 degrees, from here up, there's lots of space that I could fill in before I get to the saturation point because I haven't added any. Similar, if I'm here and I decide to add more, right? I started at 10. I don't change the temperature. I just keep adding more, adding more, adding more, adding more, adding more. Well, there's not enough room. All of this stuff is going to be super saturated or probably just sitting at the bottom of the beaker. The area below the curve represents the quantities that produce an unsaturated solution at that temperature, whereas the points above are a supersaturated solution or a saturated solution with something undissolved at the bottom. So the solubility curve that we saw back here a little bit, let's go back a bit. This one. This one shows a whole bunch of different materials, and these type of curves are always just difficult to work with, right? Usually when we have a graph, we have just one thing on the graph, and it's easier to keep track of. But here, because there are so many lines, it's so easy to get confused. So when you're trying to find anything on one of these graphs, first things first, figure out which material you're looking at, right? Figure out which material you're looking at. That other one there was potassium nitrate. Well, here's potassium nitrate right there, this one. So this is the only curve that is the same as the other one we were just looking at. The rest of this is unnecessary information. And what they're telling us in that previous picture is that there are three states of a solution: unsaturated, saturated, supersaturated. This line represents a saturated solution. Below the line is unsaturated. Above the line is supersaturated. That's what they're trying to say. All right? And that's kind of it. This is the basic idea that we're working with here, is that this graph is a way to put numbers to the idea of not full, full, more than full. And that's kind of it. There's a bunch of practice for this, although as you just saw with the examples we did, the practice is pretty straightforward. The trick is mostly just getting a handle on being able to read those graphs. Solubility curves, because we stack so many lines on top of each other, because they all use the same temperature scale and the same water quantity scale, we stack them on top of each other because they all use the same water quantity scale and the same temperature scale, which means that they're very confusing when you're first looking at them. But just try to focus down on one of them at a time. And all you're doing is figuring out the percentage. What percentage of the solute is dissolved in the solvent? Once you figure that out, you're basically gold. All right, guys, I'm going to leave it there, and I will see you guys next time, where we're going to talk about some colligative properties.